moving on to 6.1. First, this is the review of Riemann sums we just did. So take a look at that again. Make sure the general concept is clear to you. And let's take a look. So I sketched out a couple things already, so go ahead and write this down. 6.1 volumes is volumes by cross-section, what's called the disk method, and then more generally speaking, the washer method. So this is on what's called solids of revolution, and it's a way to find volumes of objects that are irregular shaped. So suppose you have, and it's not every irregular shape, but if the shape is defined by some function and you revolve it about a line, then you can find the volume of it. Okay, so let's first let this curve be y equals f of x, like that. And we want to go, so draw this out. And in the above stuff, if you do the Riemann sum on from A to B, then you end up getting this area under the curve. So think of this as area, like this. But then we're going to take that and revolve it around the x-axis. So write this out again. I just duplicated it basically, which was kind of nice. And so here's my function f, and then I'm going to sketch it in there. So that's my f of x. And then, let's maybe do gray. I'm going to take that and I'm going to revolve it. So it's going to just be a sketch, but I'm going to revolve this around the axis. So it's going to be like this is the curve. And then what you get, you got to picture that revolution coming out and then making this solid. So we want to find the volume of that. Okay, so what is the volume of that thing? So another way to look at that, to figure out the volume, is draw this cylinder. So over here, drawing a cylinder like this. So you have a circle. Okay, you can kind of fill that in, and then you do another circle, dotted. And that's a cylinder. Now what I'm going to do is break up this revolution. So you got to picture this is one sheet and it's revolving around that. And the book has pictures of this, so I can only do so good with my pen. So take a look at that. Now, what we're going to do is take this and we're going to basically put it on its edge and put it in here like this. That's going to be my little piece. It's maybe a little taller. That's the piece that I'm taking out of there. Okay, and maybe skinnier. Okay, so you get the idea, right? That's what's coming out of there. I'm going to break that up, and so what I get are these cylinders. Okay, so I want to figure out what's the volume of one of these little cylinders. So it's a thin one. So that's going to be my delta x here. And let's make this brighter. So this is going to be my delta x, like this. So that's a little piece. That's my little rectangular region, but it's not a rectangular region, is it? See? Let's do that again. Take this thing, and it's over here. So it's this piece that's in there. That piece is a cylinder, right? So volume. So we got to figure out volume of a cylinder, really. Okay, so volume of a cylinder. So volume is equal to, and I drew another picture. So we're used to maybe looking at this type of cylinder, right? So but ours is, you got to picture ours is thin. So the thickness of this thing is your delta, we're going to say is my delta x, because we're going to end up partitioning AB, right? So we're on some interval A to B, and we're going to take a partition of that. Okay, so partition AB, let's write it like that, it's probably better. So partition AB, like this. And then we're going to define our Riemann sum. But first we got to figure out the volume of a cylinder. So the volume of a cylinder is area of the base. So area of base times the height. Well, area of the base, let's change colors here, is this piece. So that's a circle, right? That's this. And then the height of this thing, so this is like your h from here to here. But this height is your delta x, right? It'll be delta x sub k because it'll be arbitrary value in that interval AB. So area of the base is area of a circle times, and this will be your delta x sub k. So area of a circle is pi r squared, right? You all know that. And then it's delta x sub k. So it's pi times the radius squared is the area of that base. So that's this. That's this area. So area of the base is that. And our height is this h, or this piece. Okay, so that's my height, right? That's this. All right, so we got to figure out the height of that thing. Or, okay, back up. We got to figure out r. So r has to be this distance, right? That's got to be my r. So whatever that distance is. So if we take that and we put it in there, what is that? So let's do that again. So you take this thing and we put it in there. So what is that height right there? What's height with respect to this? Well, height has got to be from here up to the curve. Okay, it's kind of hard to see, right? But this piece in there is up to the curve there. Okay, well, that height then, or the radius of that when you revolve it, has to be just f of x. So r is f of x. And I'm going to take that out, put it back over there. So if that's not clear, it's kind of hard to show. I don't have to be in class like demonstrating. So take a look at that. Try to see if that makes sense to you. So r is my f of x. That's the height of that piece right there. So from here up, that's the height of that little piece. From here up. And it changes as you go across. Okay, so we have all of our pieces now to do this. So we partitioned AB, and then we're going to so now we got to develop our Riemann sum. We're going to let W sub k be in the kth interval, x sub k minus 1 to x sub k. And then my delta x sub k is x sub k minus x sub k minus 1. So we're going to need that for the Riemann sum here shortly. And we have the volume of... Now, so that looks like... So basically, that's where the name, the disk comes from, is that. So that's this little piece is here. That's what that is. So it's this sliver. That's where the name comes from. So it looks like a disc. It's basically a cylinder. So the volume of the disc is, or cylinder. We'll just say V. Now using the notation we have up there, it's pi times the radius. What's the radius? It's f of x squared. So it's pi r squared, and then the delta x sub k. So that's one of them, and then we add them up. That's the sum. So now we take a limit. So we now take a limit as the norm of the partition, just like above, approaches 0. And we get the volume using the Riemann sum. We get a formula. Now I don't want you to memorize the formula. I want you to know the formula. So it's the limit, the norm of the partition approaches 0. The sum over all the k's, or you add up all those little pieces, all those little slivers. The slivers are pi f of x squared delta x sub k. And that is the definition of a Riemann sum. So if this limit exists, then we know how to integrate it exactly. We integrate it exactly with the definite integral from a to b. And then it's pi f of x squared dx. So once you do the limit, as you know, right? I know it was the last thing we were doing in Calc 1, or you were doing. This approaches, the dx represents the limit as you approach infinities, right, or approach 0, which is essentially infinite number of little partitions. So if you revolve that, this is your radius. Now it's not always going to look like that. We're going to like do different things. We're going to maybe revolve around a different line and things, but that's the start of it. That's the start of how you do this. So let's look at an example. We'll just start it here. Okay. All right. So let's take a look at this example. So I'll write it out, and then we'll finish it with the answer. So it says the region, or the setup and the answer. So the region bounded by the x-axis, the graph of y equal to x squared plus 1, x equal to negative 1, x equal to 1 is revolved about the x-axis. So that's what we just did above. Find the volume of the resulting solid. So find the volume of the resulting solid. So first thing you want to do on all of these is graph this. What are they talking about when you do this graph? And then the revolution is kind of like in your head, and you can picture it. I like to put in this, the graph, and then try to put in like a little sliver of what it would look like, right? So that's what we try to do. So let's take a look. So basically it's just this graph x squared plus 1. And so that's going to be a parabola shifted up, right? And then it's going to go from here to here, and you're going to revolve this little piece like that. Okay, so let's take a look at that. So let's put this in here. If I don't do that fast enough, it doesn't think I want a line. It's like it wants me to be messy, basically. Okay, so then we're going to take this, and sometimes I might have to draw these small, then I'll blow them up when we look at them. Okay, so we'll go up 1 unit. We'll call that 1 unit, that 1 unit, that 1 unit, and then at 2, you're going to be way up here. 4 is the problem. 1, 2, 3, 4. That's close enough. 1, and then 2, and 1, 2, 3, 4. Okay, so it's up here. So that's 2, 4. Oops, I did that a little bit wrong. That's why I didn't do it that way last time. Because I was over here, so here's 1, and then you're up 1, over 1, up 1, and then it goes high. So over 1, 2, up 1, 2, 3. So it's way up there. Okay, so we'll just draw in this piece. Okay, so it goes like this, and then it's just going to take off. So that's good enough like that. And then it goes like this, comes down. And you can still do this as a sketch, even though you're on a pad, because It just makes it look a little, your mind kind of takes over and kind of knows what to look for. And so it's like that. Okay. And it's symmetric, right? Symmetric. So that's 1, -1, and then up 1, and 1. Okay, so, but let's read what it's saying. The region bounded by the x-axis. So here's the x-axis. And this graph from -1 to 1 revolved about the x-axis. So the region in question is really this. So this is the region in question. So let's blow this up. It's like this. So this is from -1 to 1. So that's the region we're talking about here. Let's put this in. So this is being revolved about the x-axis. Okay. So what you want to do, so you don't just think in terms of a formula. You don't say, here's the formula. You got to picture what you're adding up. If you do that, you'll get this concept, all these concepts. You want to picture, okay, it isn't like, okay, it's not a disk method and then we have a formula. It's what piece are we going to use to add up the region? So it's going to look like this. Okay, so we go in here and we say, we want to revolve that, right? So we're going to take this and we're going to picture that being revolved. So it ends up looking like something like that. So we're going to take this and let me draw a different color here. And you're going to take this piece, your representative rectangle like that, and then we're going to revolve that like that around. And so this has thickness to it. Okay, so that's what you're revolving around. And so that thickness here is this thickness. So that's going to be your delta x. Oops, that's just below the thing. Let's just move that. So I'll put it up here. Okay, so that's your delta x sub k. You don't have to say sub k. It's just you just think of it as your dx or delta x. You can write either way. Generally fine with that, but you put in your dx or delta x because you need to know it's with respect to x going from left to right. All right, so then your area, so you're going to add those pieces up all the way across. So that's what you're adding, those guys. So you know you're going to add those pieces from -1 to 1. But those are what's the volume of a disk like that? And the volume of a disk is your pi r squared dx. So this is area here. And so your r is going to be that height, right? So from here up, that's the height. That's your x squared plus 1, right? So your height is that x squared plus 1. That makes sense? Not that you can answer me, but whatever. Okay, so that's x squared plus 1, and then we got to square that because we'll put that in down there. That'll be x to the 4th plus 2x squared plus 1 if you multiply that out. Actually, I don't think I showed that step, but okay, so that's equal to, you can factor out the pi, -1 to 1. And it's x squared plus 1 quantity squared dx. And then, you know what, I kind of messed up a little bit. What I'd like to do, because I didn't do it, we kind of had it up there. So what I'd like you to do is write out what this is. So volume is equal to, volume of cylinder. So volume of cylinder is equal to base times the height. So base is your pi r. These are the things you're thinking of, is pi r squared, and then your height, h, is your delta x. So it's pi, I use capitals, just use capital, pi r squared, and then that's your delta x. And then so now you picture, okay, well, what is r? What is this r? R is x squared plus 1. That's the height of that thing. That's the idea. So then now you can put that in there. You put whatever this is right here. And so that's why we get that. Okay, and then you multiply it out, etc., etc. And I won't always do all these when it's just a straight up polynomial. Pretty much easy to do. So you get pi negative 1 to 1. And I did multiply that out, huh? So x to the fourth plus 2x squared plus 1, 2x, and then work that out. Sometimes I'll do it if I have some more time, but I don't want to make these videos like way crazy too long. So I get 56/15 pi. If you're having trouble getting any of these, I'll be happy to go over them with you. We'll just do a Zoom session. I'll go over stuff with you. But basically, you're just doing 1/5 x to the fifth. You'll do 2/3 x to the third plus x, and then you evaluate from negative 1 to 1. And then you get, so it's a bunch of fractions in there. This is exactly the type of stuff I'd have you do in class to kind of practice, finish, ask me questions. So if you have any, just write them down. If it's not clear, we can go over them in a Zoom session. Okay, next we'll do a more general method called the washer method. Just leave it right there. Okay, now we're good.